Hey everybody, so today we're going to talk about linear regression. Linear regression is the idea of we're fitting a linear model, a line, to a set of data in a scatter plot. So today's objectives, you're going to determine the effect of outliers on correlation, but also on linear regression. We're going to interpret linear regression data that we are given, talk about what the slope means, what the Y-intercept means, that kind of stuff. And then we're going to use the least squares line to predict values. And then we're going to calculate and interpret residuals. So all of these things we'll talk about a little bit more. But let's start with the idea of outliers. We've already talked about correlation. Correlation is measuring the overall strength of the relationship that we see in a scatter plot for those two sets of data. So this is looking back at what I had talked about in lesson 4.1, where we looked at the relationship between shoe size and height of people. So this is our scatter plot from the last lesson, and the correlation coefficient for that data was R equals 0.95, which is pretty strong. Remember, the highest possible correlation you can get is 1, so that's very, very strong. So suppose we took away the point that's a shoe size of 15 and a height of 75 inches. So that's that point way up there, which is a little bit kind of removed. We can maybe call it an outlier. So we want to know, would that change the correlation? So if I took that point away, made it disappear, right, would that change the correlation? So in this case, probably not by much, because that point that we saw there is kind of following the pattern. It's not anything that's out of the ordinary. It's following the pattern of the rest of the points. So in fact, our new correlation, when I take that point out, is R equals 0.93. So it slightly changed, but we would still call that very strong and a positive linear association. So that one point being taken away didn't change things much. So even though you might call it an outlier because it's a little bit further away from the rest of the data, it's not changing things to take it away. So let's look at, now I have this set of data. Remember, our current scatter plot has a correlation of R equals 0.93 after I took that point away. So suppose we added another student's data who had a shoe size of 8 and a height of 75 inches. So that's up here. So I've just added that point. Would that change the correlation? Okay, so this point does not fit the pattern of the rest of the points. This is a much smaller shoe size for that height that we would expect. So that point right there probably will change the correlation because it doesn't follow the pattern, right? So in fact, our correlation coefficient ends up being 0.4. So all because of that one point, we ended up with a much, much weaker correlation. So outliers that are kind of above and below that don't fit the pattern of the data can end up having a pretty big effect on the data. So there's this link that's in the kind of speaker notes if you look at this slideshow later, that brings you to this page right here, which is a really good way of kind of demonstrating or practicing with correlations. So I'm just going to put a bunch of points on here, just clicking. So I end up with this kind of really strong correlation. It's not perfect, but I want to look at what happens. Actually, I may do this. Hold on. Put these closer to the left side so I can show you. So I've got this strong correlation, moderately strong in the 0.8 region. So again, if I add a point over here that fits the pattern of the data, right, it doesn't, and in fact, it kind of strengthens the correlation. So it doesn't make it worse, it changes it a little bit. But when we're talking about data that's fitting the pattern, it's not going to weaken the correlation a whole lot. Compared to, right, if I'm going to put this back over here with the rest of them. If I had a point that's above or below, right, that has a much bigger effect on correlation. And you can kind of see what happens as I drag that point kind of in there with the pattern, and then over here, we're seeing how much that correlation coefficient changes. And then on top of that, if I draw my line of best fit, we can see how kind of changing things, looking at how it changes the pattern, right? It's much more significant when it's not in the pattern of the rest of the data. When we're in the pattern, it's not changing that line very much at all, but when we are out of the pattern, right, it has a much bigger effect on correlation. So that's just a fun little website to play with to kind of help you understand how outliers can affect correlation and our least squares regression line. Right. So let's move on. So a lot of what we are doing when we're dealing with linear regression stuff is we're interpreting some of the values that we see. So I just did this on the website. I don't think I have that in the comments yet, but I'll put it there. This is the same website we were using last class to find correlation, and we'll also use it to find the least squares regression line. So this is looking at a set of data. I put this in there. This is looking at people's how much sleep they typically get on a weekend or a weekday, and then how much sleep they typically get on a weekend. So I have that data in here. And then I made a scatter plot so I can see that scatter plot has a generally positive association. Typically, people as they get more sleep during the weekday, they tend to get more sleep on the weekend. That makes sense. We have our correlation coefficient right here. And then I also clicked the button to calculate the least squares regression line on that website, and it gave me my equation for the line of best fit. All right. And then we also have a couple other values that we'll talk about. So firstly, when we look at the slope, so we have our equation right here. The slope is the one that says right by the x in that equation. So the slope is the 1.2995. So what the slope represents, if you think back to what slope is, it's rise over run. The way we interpret it in words is we talk about it as this is what happens to y when your x increases by 1. So it's how much is it rising as the run goes over 1. So it's rise over run. So what we say just is a little bit more fancy terms, but same idea. It represents the marginal change of the response variable, the y variable, for every unit change in the x variable. So for our sleep example, we're going to say as x goes up by 1, this is what y is going to do. So for every increase of 1 hour in weekday sleep, because that was on our x variable, was weekday sleep, that was our explanatory, we expect to see an increase or decrease, a change of 1.2995 hours in our y variable, which is sleep on the weekend night. All right, and because our slope is positive, we can say we expect to see an increase of 1.2995 hours and sleep on a weekend night. So for every 1 extra hour of sleep someone gets on a weekday, we're expecting to see about 1.2995 more sleep hours on a weekend night. Even just looking at the graph, I can see that we have that positive association. So I would expect slope to be positive, right, just based on the graph, and it is. Right? So that's how we interpret the slope. For every 1 unit change in x, this is what we expect to happen to y. That's what slope tells us. So let's now talk about the y-intercept. So the y-intercept in our regression output is the number that's all by itself, right? That doesn't have the x next to it. So in this case, it's negative 0.48598. Right? We could round that. It's not a big deal. But remember, your y-intercept is telling us where this line, this regression line, would cross the y-axis. So in other words, it's the value of y that we would expect when x is 0, because that's what happens on the y-axis. X is 0 and y is a number. So the way we would say that in words is that it represents the expected value of the response variable, the y variable, when the explanatory variable is 0. So when x is 0, this is what y is expected to be. Okay, the y-intercept isn't always meaningful in a real-life context. So for the sleep example, we could say when x is 0, so for a student who sleeps 0 hours on a weekday, because that was our x, was weekday sleep, would be expected to get negative 0.4859 hours of sleep on a weekend. So for a student who sleeps 0 hours on a weekday, they're going to get negative 0.4859 hours on a weeknight, all right, or a weekend. Right? Is that meaningful? Not really, because it's impossible to sleep a negative number of hours. So the y-intercept is sometimes a little weird. It may not always represent a real life situation. It's just there to make the equation work for the majority of the points in our data. So that is something to keep in mind. So now let's look at if we wanted to make a prediction. And we can already see the answer because I messed up on my transitioning on this slide. All right, so our linear regression equation in context. So we have the equation right here that was given to us in the computer program. But when we put it in context, that means we're going to write it, instead of using y and x, we're going to actually put what those variables are in the equation. And that'll make it a little bit easier to use to make predictions. So there's my equation. We're going to put it in context. So weekend sleep was my y, and then weekday sleep was my X. Notice that I put the word predicted, or you might put the word expected in front of that. You'll notice in that equation, there's a little hat, circumflex situation on top of that letter. And what that hat represents is that it is predicted. This is the expected or predicted amount of weekend sleep based on how much weekday sleep someone gets. So we can use that model to predict what other students' weekend sleep hours might be based on their weekday sleep hours. So if we wanted to predict the amount of weekend sleep for a student who sleeps about 7.5 hours on a weekday, I could use that equation and plug in the values. So predicted weekend sleep, we're going to plug in a negative 0.48598 plus 1.2995 times, right, their weekday sleep of 7.5. Put that in our calculator. That's going to give us 9.26 hours. So a student who sleeps 7.5 hours on a weekday is expected to get about 9.26 hours of sleep on a weekend. So it's a way for us to make those predictions. Forgot I had a thing for that. So a student who sleeps 7.5 hours on a weekday, typical weekday, is expected to sleep for 9.26 hours on a typical weekend. We talked a lot about correlation in lesson 4.1, but just to reiterate, our website here gave us the correlation in R. So R equals 0.691. So just as a recap, would that be low, moderate, or strong in terms of strength? We'd probably call that moderate. Remember, 0.8 and above is strong, 0.5 and below is low or weak. So this is kind of in the middle, so we'd probably call it moderate. Is it positive or negative? This would be positive. Remember, R is going to be positive when the association of the graph is positive. R is going to be negative when the association of the graph is negative. Right? And also should match the slope sign. So our slope is positive, which makes sense that our R is positive. The other thing that we can talk about in terms of strength is what we call the coefficient of determination, which is a really, really fancy word or term. But basically, this is just another measure of strength, and it is represented by R squared. Now, our computer program gives us R squared. Your calculator will as well. But R squared is literally just that R value squared, so times itself. So if I did 0.691 times 0.691, this is what I would get, but they gave it to us as a separate value. So the way we talk about coefficient of determination, it's the R squared, and what it represents is the percent of the variability or the change in the response variable that is explained by the explanatory variable, which is a weird thing to talk about. So it's a weird kind of understanding or message of strength. But let's go ahead and put it in our sleep context, in our sleep example. So our R squared was 0.478 times by 100 to turn that into a percent means that about 47.8% of the variability or the change in the weekend sleep is accounted for or explained by our linear regression model using weekday sleep. So in other words, right, the change that we're seeing in weekend sleep, some of that, about 47.8% of that change, is explained by how much weekday sleep you get. The other, however much percent is left, right, is the unexplained variation. In other words, that other percentage, the leftover, if we subtract it from 100%, right, which is 52.2%. That other 52.2% of the change in weekend sleep is due to other things. There are other things that affect how much weekend sleep you get. How much homework did you save for the weekend that you now have to do and stay up all night? How much do you hang out with your friends? Do you stay up late playing Among Us or watching YouTube videos or chatting with your friends? So other variables that are affecting how much weekend sleep you get, that's that unexplained variation. So it's another measure of strength. It's telling us how much of this variation that we're seeing actually has to do with this linear model and how much of it is unexplained that's due to other factors. So it's another measure of the strength. So we're going to talk a little bit more about making predictions. So this is data, again, weekend sleep or weekday sleep versus weekend sleep, same stuff we've had before. So go back to predictions. Remember our formula, that we had, predicted weekend sleep is equal to negative 0.48598 plus 1.2995 times weekday sleep. So if we wanted to predict the amount of sleep hours, weekend sleep hours, for a student who gets 20 hours of sleep on a weekday, I don't know how they're managing that. They're sleeping all the time. But if they get 20 hours on average on a weekday, their predicted weekend sleep would be negative 0.48598 plus 1.2995 times 20, which comes out to 25.5 hours of sleep. So a student who sleeps 20 hours on a typical weekday is expected to sleep for 25.5 hours per day, per night, on a typical weekend day. Are we comfortable with this prediction? Not really, mainly because 25.5 hours in a single day is not possible. But basically what happens here is we're comfortable making predictions that are within the original range of data. So if I look at my data, weekday sleep hours are going from 5 to about 12, right? That's kind of the range of our data. So we can use our linear regression line, our line of best fit, to make pretty decent predictions within that range. But as soon as we go outside of that range, our predictions are not going to be as reliable, right? And the reason for that is we don't know that this linear model that seems to work fairly well for values within that range, we don't know if that same linear model is going to last forever. In real life, regression models, especially linear ones, are not going to stay that same forever. Things don't like increase continually the same rate forever and ever and ever. If you think about your height, right? Your height grows really quickly and rapidly when you're young, but as soon as you hit like 17, 18, it changes depending on what biological sex you are, but like at some point you're going to stop growing, right? So it might be linear and it might be a really big slope at first, but at some point it's going to measure off or level off. So we can't make predictions, or we're not going to be comfortable making predictions that are outside of the original range of our data, right? And we have a word for that. So interpolation is something we're comfortable with. Interpolation would mean that we are making predictions within the original set of data. So interpolation. And then we're less comfortable with extrapolation, right? Because that would be making predictions that are outside of the original range of data. So extrapolation or extrapolation, whatever you want to call it, means that we're trying to make predictions for values that are outside of the range of X values that we have in our data. And it's just going to be really unreliable because we don't know that linear model we're seeing for that set of data, we don't know if it's going to continue in that same fashion on either side. So we have to be careful. All right, next little main topic. We are almost at the end of the slideshow if you're curious. We're going to talk about something called a residual. Right? So a residual is the difference between the actual and the predicted Y values. So the difference between the actual and the predicted Y values. One thing that I talked about in at least one of my classes on lesson 4.1 is we talked about the fact that our line of best fit does not go through all the points. In fact, most of the time, line of best fit will miss the majority of the points. The goal of that line of best fit is to try to get kind of in the middle. We generally want about half of the points to be above the line and about half of the points to be below the line, more or less. So if our line is not hitting a lot of the points, that means our line is going to be off in terms of its prediction. Maybe by a little, maybe by a lot. So one student, it says, got 12 hours of sleep on a weekday and 16 hours on a weekend. So that's this point right here up at the top. So if we wanted to calculate that student's residual, okay, residual is basically the actual Y value for that student minus the predicted Y value for that student. It tells us how far off is our prediction from what actually was true for this specific set of data. Okay, so the first step of that is to figure out what would be the predicted value, and that comes from the equation. So I'm going to use my equation. Predicted weekend sleep is equal to negative 0.48598 plus 1.2995 times 12, which was their weekday sleep hours. And that gives me 15.11. So that student would be expected to get about 15.11 hours of sleep on the weekend. Okay? But actually, the student gets about 16 hours of sleep on a weekend night. So when I find my residual, right, we're doing our actual Y value. Our Y was weekend. So actual weekend sleep minus predicted weekend sleep. So 16 was their actual weekend sleep minus 15.11 was their predicted, sorry, I just lost my train of thought, weekend sleep. When we subtract those, we get positive 0.89. So what this would tell us is that this student gets about 0.89 more hours of sleep than we would have expected them to get based on their weekday sleep. Okay, so they're a little bit above the prediction. So that prediction actually a little bit underestimated what they were going to get on the weekend in terms of sleep. So the residual is negative. That means the point is below the line. So the line, which is our prediction, is overestimating or over predicting. When the residual is positive, that means the point is above the line. So that means our model, which is the linear regression line, is under predicting or underestimating what is true for that particular value. So it seems kind of opposite in terms of like what it's predicting, but just remember residual is positive means the point is above the line. Residual is negative means the point is below the line. And the line is the prediction. Last thing we're going to look at is nothing new in terms of interpreting. This is like the same stuff. But I wanted to show you real quick, sometimes when we are given the information that we need, they may not ask you to calculate it. They may just give you the information, but they might give it to us in this kind of weird format like this. So you have a whole bunch of numbers that you have to look at. Some of them are kind of labeled, like r squared is right there, but the rest of it is not. So one thing we want to look for in this little equation, firstly, I'm only ever going to look at this first column of numbers. The rest of these numbers we're ignoring. And then when we look at that first column of numbers, one of the words in that little table under the word predictor, we see the word height. So this is a statistical software package that looks at, this is looking at linear regression for people's weights versus their heights. So I see the word height in that table. What that means is that height is the x variable. So whatever numbers in that table or letters, words in that table, that's the x variable. And most of the time they'll tell you that which one is x and which one is y. But the height is the x, okay? And the number next to that is your slope. So 6.1376, that is slope. Okay? The other number, most of the time it's labeled constant, right? That's going to be your y-intercept. So when I write my equation for that linear regression, right, my y value, if height is x, then that means weight must be y. And again, most of the time you're told which one's x, which one's y. So predicted weight is equal to y-intercept, negative 266.53, plus slope, 6.1376, times x, which is height. So that would be my equation. So that's how we kind of pick out those numbers from that table. So 6.1376, that is the slope. So when we interpret slope, we say as x goes up by 1, this is what y is predicted to do. So for each increase of 1 unit in our x's height, we expect an increase, because it's positive, of 6.1376 units in weight. That should say weight. It does not. I'm going to fix that right now before I forget. Give me a moment. Sorry. I just know that's going to confuse me if I don't fix it. So for every 1 unit increase in height, we expect an increase of 6.1376 units in weight. And then for the strength, remember the strength comes from R, which is correlation. We don't have R, we have R squared, which is 89.7%. So R squared is 0.897. Remember, it's already a percent. So we kind of have to divide by 100 to turn it back into its decimal form. So 0.897, we take the square root of that, we get, there we go, 0.947, right? So if we already have R squared and we wanted to know R, we just work backwards, we square root it. So 0.947, which is a strong correlation. Okay. So that is a little bit of how we kind of read some of that information that we might be given in this format. It's not always, but if you're given that kind of table, that is how we read it. Okay, that is it for today. I will see you guys in class next.